Hello everyone, welcome to my YouTube channel SGKmistry lectures. In this video I'll be explaining about certain subtopics under the topic solid state, and I'll be covering the topics such as the different types of solids, the classification of solids into different types such as molecular solids, ionic solids, covalent solids, etc. And also I'll be speaking about the different types of crystal lattices, and also I'll be speaking about Bragg's equation in detail. So first let me come to the basic classification of, or I can say the types of solids, where we classify solids into two major categories, that is amorphous solids and crystalline solids. So what are the differences between these amorphous as well as crystalline solids? So here we have the basic differences between these two categories. So first one is, in crystalline solids there is proper arrangement of particles. There is a definite arrangement of particles in the crystalline solids, and that's why they have a definite geometry. Whereas in case of amorphous solids, there is no proper arrangement of particles in the solids, and that's why the amorphous solids do not have a definite geometry. So this is the first difference between these two categories of solids. One more difference is in terms of the order of arrangement of the particles. So here in case of crystalline solids, they have a long range order, whereas in case of these amorphous solids, they have a short range order. That is, as I've already told, the arrangement of particles in these solids, here in case of crystalline, since there is a definite arrangement in three-dimensional space, these crystalline solids, they have a long range order, whereas in case of amorphous solids, since there is no definite arrangement, they have a short range order. So here in case of crystalline solids, they melt at a particular temperature. That's why we tell that the crystalline solids have sharp melting point. Whereas in case of amorphous solids, they start melting at a particular temperature, and they go on melting and then completely convert into the liquid form after a particular range of temperature. So that's why the amorphous solids, they do not have a definite melting point, or I can say they melt in a particular range of temperature. So this is one more difference between the crystalline and the amorphous solid. The last difference, I can say the important difference between these two. Here in case of crystalline solid, they are anisotropic in nature, whereas the amorphous solids are isotropic in nature. Now what is this anisotropic and isotropic? Anisotropic, why we call this crystalline solids as anisotropic? Because here, as I've already told, there is a definite arrangement of the particles in three-dimensional space, and that's why when you measure any particular physical property, okay, let us say for example refractive index. When you measure the refractive index, which is a physical property, you see that when you measure this refractive index in different directions, you get different values for the refractive index. That's why we tell that the crystalline solids are anisotropic. Now why do we get different values when you measure this refractive index in different directions? This is because here there is definite arrangement of particles. So now you can just imagine, if you have the definite arrangement like this. So if the measurement is done in this direction, here you can see that it is passing through two different particles. If it is done in this direction, here there are no particles at all in this direction. So that's why the measurement in these two different directions will give you different values. Whereas in case of amorphous solids, there is no proper arrangement of particles. So what happens, since there is a random arrangement, so even if you measure these physical properties in any direction, you will always get the same value. So that's why these are isotropic, whereas the crystalline solids are anisotropic in nature. The examples for crystalline solids are the most common ionic solids such as sodium chloride, potassium nitrate, copper sulfate, and whereas in case of amorphous solids, the simple example is glass, and also other synthetic polymers which have high molecular weight. And one more a common name for these crystalline solids and these amorphous solids is that since there is definite arrangement of particles in three-dimensional space in case of crystalline solids, we call these crystalline solids as true solids. These are called as true solids. Whereas the amorphous solids, since there is no proper arrangement of particles, there is no definite arrangement of particles, we call these amorphous solids as pseudo solids or false. Pseudo is nothing but false. So these are true solids, whereas the amorphous solids are called as pseudo solids. So this is the basic differences between, these are the basic differences between the crystalline and amorphous solids. Next, coming on to the classification of solids. Mainly there are three different types of solids. First type of solid is molecular solid. So under molecular solid we have polar molecular solids, non-polar molecular solids, hydrogen bonded solids. So these are the different types in under molecular solids. Then we have the other categories, that is covalent solids, ionic solids and metallic solids. So overall we have these four categories, molecular solids, under which there are three categories, and then we have the covalent, ionic and metallic solids. So coming on to each of this one by one, let me just tell the important characteristics of each of this. So polar molecular solids are nothing but here they contain the constituent particles that are polar in nature. Now what is this polar molecule? So let us take one example. Let me take a molecule AB, where the difference in electronegativity between these two atoms, atom A and atom B, is very high. Let me say one is completely electronegative, the other one is completely electropositive. So suppose if A is electropositive, this will be delta plus. If B is electronegative, it will get a partial charge, delta minus. So here there is a separation of charge between the two different atoms of a molecule, and that's why we can call these also as a dipole. So how these different molecules in these solids are held together? They are held together by dipole-dipole interactions. A particular molecule here which is having two different atoms of different electronegativities, we can call it as a dipole. So all such molecules, when they are held together, they are held together by dipole-dipole interactions. So one of the common example for polar molecule is HCl, where H is electropositive and Cl is electronegative in nature. So HCl is a polar molecule. Next, coming on to non-polar molecular solids or non-polar molecules. Here, in case of non-polar, so polar you already know, the two atoms in a molecule will have different electronegativities, whereas in case of non-polar molecules, the two atoms forming the molecule will have almost equal electronegativities. So most common or most easy example here to remember is in case of non-polar molecules, you can give examples such as H2, where both are hydrogen atoms and both have equal electronegativities. You can also give other examples of diatomic molecules, where both homodiatomic molecules, where both atoms are same and they have equal electronegativities. Or even you can go for heterodiatomic molecules, where two atoms are different but their electronegativity difference should be lesser. Or I can say they both should have almost equal electronegativity values. Next is hydrogen bonded solids. Here, in case of hydrogen bonded solids, the different molecules are held together by hydrogen bonds. The very most common example which I can give here is NH3. We have ammonia, that is NH3. So NH3, single bonds, that is nitrogen is single bonded with 3 hydrogens. So 3 bonds with 3 hydrogens, and it also has a lone pair here. So hydrogen bond is nothing but here there is a force of attraction between the electropositive hydrogen, which is attached to an electronegative atom, and the electronegative atom of the other molecule. So again, in hydrogen bonding we have two different types. intramolecular hydrogen bonding and intermolecular hydrogen bonding. Here, in case of ammonia, we can say there is intermolecular hydrogen bonding. Intermolecule is nothing but the hydrogen bonding between different molecules. So here we have electronegative nitrogen atom, electropositive hydrogen atom. This is one molecule of ammonia. So let us imagine there is one more ammonia molecule. Okay, one more NH3 molecule nearby. So this hydrogen and this nitrogen can have a weak force of attraction between them because N is electronegative and hydrogen is electropositive, and this hydrogen is again connected to electronegative nitrogen. That's why this force of attraction that is present between the hydrogen of this ammonia and nitrogen of the other molecule of ammonia, that is called as hydrogen bond. So such type of molecules where the different molecules are held together by hydrogen bonding are called as hydrogen bonded solids. Next, covalent or network solids. Here the different atoms are held together by covalent bonds. The most simple molecule or most simple compound which I can tell here, the example which I can quote here is diamond, where the different carbon atoms are held together by strong covalent bonds, and thus the diamond, you already know the characteristics of diamond, it is very hard. And here, why it is very hard? Because all the carbon atoms are held together by strong covalent bonds. Next, coming on to ionic solids. Here what happens is the different ions, that is cations and anions, are held together by electrostatic force of attraction or the ionic bond. Mainly this ionic bond is very strong because it is the attraction, electrostatic force of attraction between the positively charged cation and the negatively charged anion. So positive charged cation and the negatively charged ion will have the force of attraction between them because of their opposite charges, and such type of compounds where the ionic bond exists between the ions are called as ionic solids. The most simple examples are the ionic compounds such as KCl, NaCl, potassium nitrate, etc. Last is the metallic solids, where obviously the atoms are metal atoms. So here you already know about the structure of the metals, that is how the electrons and how the metal ions are arranged in case of metals, that is the kernels, the metal kernels are arranged and the electron C surrounds these metal kernels. So that is how the arrangement of particles is present in these metallic solids. So this is about the two important classification of solids, that is the crystalline and amorphous solids, and also the main classification of solids into molecular solids, which has three different categories. Then we have the covalent solids, ionic solids and the metallic solids. So next I will be explaining about the types, what is meant by the crystal lattice, and also the different types of unit cells. Yeah, so coming on to the next topic, that is what is meant by unit cell. So unit cell is nothing but the smallest portion of the crystal lattice, that is when this particular unit cell is repeated so many times, repeated many times in three-dimensional space, then it finally leads to the crystal lattice. So I can say the entire crystal lattice is made up of innumerable number of these unit cells. So now when we are speaking about this particular single unit cell which repeats itself to give the entire crystal lattice, that unit cell is of different types. So mainly these unit cells are of two important categories, that is primitive unit cells and centered unit cells. So what are these primitive unit cells? In primitive unit cells, the particles can be anything, maybe ions, molecules or atoms. So let me just tell in common, I can say the particles that are making up the unit cell. So they can be of any type. So the particles in case of primitive unit cells are only present here in the corners of the unit cell. You can see here whichever I have marked. So they are present only in the corners and they are not present in any face or on the edges or anywhere else, but only on the corners. Then such type of unit cells are called as primitive unit cells. The other type of unit cells are centered unit cells. So from the term itself it is very clear. So along with the particles in the corners, there are certain other particles that are present in the center, maybe center of a face or center of the edge or whatever it is. So let us see which are these different types of centered unit cells and where are these particles present in the unit cells. So in centered unit cells, there are three different types, that is body centered unit cell, end centered unit cell and face centered unit cell. So you can see I have given the representation for these three different types of centered unit cells. So first one is body centered unit cell. In body centered unit cell, the particles are present in all the corners, that is all the 8 corners. Along with that, one particle is present in the center of each of the cube. So this type of unit cell is called as body centered unit cell. Next, coming on to end centered unit cell. So here the particles are present in all the corners of the cube. Along with that, they are present in any of the two opposite faces. So you can see here the particles can be present here opposite to each other, any two opposite faces. Either they can be present here or these two opposite faces. Next, face centered unit cell. Here the particles are present in the 8 corners of the unit cell. Along with that, they are also present in the center of all the faces in that particular unit cell. So here you can see this is the upper face. So center of that particular face, you have one particular, in the center you have one particle. Here also there is one particle at the center of this face. So here at the side. So there are totally 6 faces for a particular cube, and in the center of each of these 6 faces there are the particles that are present. So such type of unit cells where the particles are present in the corners of the cube or corners of the unit cell, along with that even in the center of each of the faces, that center of each of the 6 faces is called as face centered unit cell. So next, coming on to Bragg's equation. So why do we need this Bragg's equation? So Bragg's equation is used in order to calculate the interatomic distance between, interatomic is nothing but the distance between the atoms or distance between the particles in the crystals. So how do we find it? Experimentally how it was found? So here Bragg's equation was formulated by making use of X-ray diffraction studies. So by X-ray diffraction, the interatomic or interparticle, the distance between the particles was calculated, and the Bragg's equation was given as n lambda is equal to 2d sine theta, where n is the order of reflection, whereas lambda, since they have used X-ray diffraction studies, lambda is the wavelength of X-rays, then d is the distance between the two planes, interplanar distance, and theta is the angle of reflection. So once we know here the other terms, that is order of reflection or the wavelength of the X-rays, then you can easily find out what is the distance d, that is the interparticle distance or the interplanar distance that is present in the crystal. So here we can see here, as the order of the reflection increases, even the theta, that is the angle of reflection, also increases. They are directly proportional to each other. Suppose if the order of reflection is 1, then the equation reduces to lambda is equal to 2d sine theta. Suppose the order of reflection is 2, then the equation becomes lambda is equal to, this 2 comes to the denominator, so lambda is equal to d sine theta. Suppose the order of reflection is 3, then the equation becomes lambda is equal to 2 by 3 d sine theta. So if the order of reflection is n in general, then the equation, the Bragg's equation becomes lambda is equal to 2 by n d sine theta. So this is the general equation which can be used to determine the interplanar distance in crystals by making use of X-ray diffraction studies. Next is contribution of lattice points per unit cell. That is how we have to calculate the contribution of the lattice points per unit cell of these different unit cells, maybe the face centered, body centered, or the simple cube, or this end centered unit cells. So let us see here how each of them, now we know that in a particular, when we count here, So here there are 8 particles in the corners. Along with that there are 6 particles in each of the center of the faces. But how much of these particles actually belongs to one particular unit cell? That we are going to calculate by this formula. So now we know that each of the corners are nothing but these which I have shaded. So the corners, each corner is shared between 8 different types of unit cells. Now here you can see unit cells are nothing but it is the basic unit of the entire crystal lattice. So obviously along with one unit cell there are all other unit cells in all directions. So suppose you take, this is the unit cell, there will be a unit cell this side, front, behind, upper, here below, as well as on the other side, left, right, the upper and below side. So in all directions there will be other unit cells which are repeated to form the crystal lattice. So one atom or one particle that is present in the corner is shared between 8 other surrounding unit cells. So what is the contribution of this particle to this unit cell? That is 1 by 8. So 1 by 8 is the contribution of one atom which is present in the corner. Same way, if you are considering the atom which is present in the center of the face. So obviously this face is shared only by 2 unit cells. Here you can see this face, it is shared between this unit cell and the upper unit cell. So the contribution is 1 by 2. Next, body centered, if you check, this atom or this particle belongs entirely to that particular unit cell. So it is not shared with any other unit cell. So the contribution of body centered unit cell, that is the contribution of the particle which is present in the center of the unit cell is 1. It is not shared with any other unit cell. So now let us calculate, based on this concept, let us calculate the contribution of each of the particle to those respective unit cells. So first coming on to simple cubic. Simple cubic is nothing but the primitive unit cell where it has the particles only on the corners and not in any of the faces or the center of the units or anywhere. So it is only present, the particles are only present in the corners of the unit cell. So here we have 8 atoms in the 8 corners. So total number of atoms are 8 and contribution of each atom is 1 by 8. So there is no atom in the face center. There is no atom that is present in the center of the cube. So here we have 8 into 1 by 8, which is nothing but totally we have only 1. So these two 8 cancel with each other. Next, for face centered unit cell. So here we have, there are 8 atoms in the 8 corners. So in the corners we have 8 and the contribution of atoms in the corner is 1 by 8. So 8 and 8 will cancel with each other. Face center, there are 1, 2, 3, 4, 5, 6 atoms in the center of each face and the contribution is 1 by 2. So 2 and 3, there is no atom in the center of the unit cell. So this is nil. So here we have 1 plus 3, that is 4. So total number of particles that are present in the face centered unit cell is 4. Next here, coming on to body centered. BCC is nothing but body centered cubic unit cell. So here we have 8 atoms in the 8 corners. So 8 into, the contribution is 1 by 8. So 8 and 8 will cancel with each other. Next, there is no atom in the face center and there is one atom in the center of the body of the unit cell. So we have 1 and the contribution of the atom which is present in the center of the body is 1. So 1 into 1, it is nothing but 1. So 1 plus 1 will give you 2. Yeah. So next coming on to end centered cubic unit cell, which is nothing but ECC. So here there are 8 atoms or 8 particles in the 8 corners. So as usual we have 8 and the contribution is 1 by 8. So 8 and 8 will cancel with each other. There are 2 atoms here at the end, any of the 2 opposite faces. So here 2 atoms or 2 particles which are again shared with 2. That is, one particular particle is shared between 2 unit cells. So here there are 2 such atoms and it is shared with two other unit cells. So 2 and 2 will cancel with each other. There is nothing as body-centered atom or body-centered particle in this unit cell. So we have 1 plus 1, that is 2. So the total number of particles in the end-centered unit cell is 2. So this column gives you the exact number of the number of particles that are present completely belonging to those particular unit cells. So this is how we calculate the contribution of the lattice points to the per unit cell. How much of that particular atom or particular particle is completely belonging to that particular unit cell in which it is present. So with this, I will conclude the video, and in my next video I'll be explaining about close packed structures, how the arrangement of solids is taking place by the combination of atoms or the combination of particles, and also I'll be explaining about different types of defects that are present in the solids. I thank you all for watching the video.